webinar series, which is brought to you by the IDEAS Productivity Project, funded by the Exascale Computing Project, in collaboration with the U.S. Department of Energy Computing Facilities, the Argonne, Oak Ridge, and Lawrence Berkeley National Laboratories. I'm Osni Marquez from Lawrence Berkeley Lab. Ashley Barker from Oak Ridge and I will be the hosts for today's webinar, Discovering and Addressing Social Challenges in the Evolution of Scientific Software Projects. And the webinar will be presented by Rene Gassmoeller from the University of California at Davis. Rene is a project scientist at the Computational Infrastructure for Geodynamics at UC Davis. His work focuses on the interaction between mantle convection and plate tectonic processes, numerical methods for geodynamic modeling, and sustainable software development in the Earth Sciences. He was awarded a PhD in geophysics from Potsdam University in Germany, in cooperation with the German Research Center for Geosciences. Rene is a 2019 Better Scientific Software BSSW Fellow. As you can see, there is a call out there. This is a slide. And the fellowship gives recognition and funding to leaders and advocates of high-quality scientific software. And the applications for 2020 are now open. So if you go to that website, bssw.io/fellowship, you have more information about this the fellowship. So all attendees have been muted. We'll be receiving questions through the WebEx chat and also the Google Doc that the link has been pasted in the chat. And the webinar will have breaks, so the speaker can respond to questions that come in. So with that, I will stop sharing here and give sharing privileges to you, Rene.
Okay, thank you, Osni. Let me get set up here. Do you see my slides?
Yes.
Okay, great. So good morning, everyone. Thank you, Osni, for the introduction, and thank you all for joining this webinar. Instead of the lengthy title that I gave to the webinar series, I tried to make it a bit more succinct on this slide. In this talk, I want to talk about better scientific software communities, finding and addressing social challenges in the evolution of software projects. And to give you a bit of background about myself and my perspective on these questions, I will separate my talk into two different parts. First, I will talk about why we should talk about software communities and social challenges. And the second part is about what is BSSC, Better Scientific Software Communities. As Osni said, my background is in computational geophysics. I am one of the maintainers for a software called ASPEC, the Advanced Solver for Problems in Earth's Convection, which is a computational fluid dynamics solver for computational geodynamics. And to give you an idea for the kind of computational fluid dynamics problems we are solving, I brought a little animation. So this is one of the models that we do with ASPEC. What you see here is essentially a rock in the Earth interacting with the movement of tectonic plates at the surface. And when you take a look at the top right panel, you see essentially how a new oceanic crust is formed. In this example, in particular in the South Atlantic, close to the island of Tristan da Cunha. If you separate HPC codes on a scale between small scale and large scale codes, we are somewhere in the middle. Our typical models run on a few dozen to a few thousand cores. This particular model ran on 750 cores and took maybe around 15,000 CPU hours. So I'm a computational geodynamicist, and when I started my PhD, I became one of the users of the software aspect. And then I started developing new features for it. I became one of the developers, and 5 years ago, I became one of the maintainers of the project, of the now 4 maintainers of the project. And in that time, over the 7 to 8 years, I witnessed a pretty impressive growth of the project. So when I came in, it had maybe 4 users. It was just started. And by now we have well over 100 users, and many of them also contribute to the code. And that might seem not much to some of you who work in big domains, but in the domain of computational geodynamics, that is actually quite a percentage, maybe 20% of the computational geodynamicists who are around. I am now at the Computational Infrastructure for Geodynamics, as Osni said, and that's a project that tries to support and distribute best practices in computational geodynamics and computational earth sciences in general. And in this job, in this new position, I not only work with Aspect, but I also work with a number of the other CIG software projects and try to help them implement best practices. And as Osni said, in 2019, I was awarded the BSW Fellowship in order to spread this idea of software communities. If you're interested in my other projects, I have a GitHub page, and you can find a lot of information there. And I put some figures of my scientific work at the bottom of the slide. So I mentioned my job is to spread and support projects implement best practices. And there are plenty of tools nowadays that help us to implement these best practices for software projects. There are tools for version control, there are tools for code review and collaboration, lots of tools for testing of code, portability, documentation, reproducibility, scalability. And we not only have all of these tools available, there's also a lot of information available about how to use these tools. The Better Scientific Software website has regular blog posts. There is this webinar series by the IDEAS project. There's the Software Carpentry, who teaches basic lessons about sustainable software. The Computational Infrastructure for Geodynamics has its own list on geodynamics.org. And there are also all sorts of publications, journal articles, or whole books written about how to design a successful and sustainable scientific software project. So if you take a look at all of this, then you could think we learned our lesson. We know how to build good software and sustainable software. So what can possibly go wrong as you start a new project? Well, as we learned within our project and within all of the projects that I supported or consulted with, actually a lot of things. A project is more than just the software that you are working on. It's more than the source code and the data. It's a community. And this community is diverse. It's often unpredictable. You don't know who will join your community and what they want to do. And the leaders of the software project need to take that into account and, in case, reevaluate their goals or adjust the policies of the project. There was also a timely BSW blog post just a few weeks ago by Wolfgang Wangers, where he argues that leading a scientific software project is a lot about personal decisions made by the maintainer. And at this point, I want to take a quick break and talk about a few definitions, because there are a few terms that I will use throughout this talk that I want to explain with. When I talk about a user, that's still pretty simple. A user is a person who uses your software for some purpose, either science or teaching or presentations, something like that. Now, a developer is a person who actually changes your software. And this developer can be a user, but it can also be a person who is just paid to do the development work. And then there's a separate category that I call the maintainer. You could also think of these as leaders, but the important part about the maintainer is that they do infrastructure work for the software. They care for the project as a whole. They do work that is not directly related to features. And again, maintainers can be developers and users, but they don't necessarily have to. And then when I talk about community, I mean everyone involved in the project. And that involves the maintainers and the developers and the users, but it can also involve people who are not directly working on the project, but just providing funding. Think of a PI who has some students who work on the project. The software, again, is relatively simple to define. That's the source code, all of the tests, and the documentation that you have for this software. But when I talk about the software project, then I mean not only the software, so the digital version of the software, but also the community. And if you take anything away from this talk, then please let it be this bullet point, that a software project consists of both the software and the community that uses and develops this software. And at this point, I want to take a first quick break and see if there are any questions.
No, Rene, not at this point.
Okay. Then I will continue for now. There will be a few further breaks later. Okay, so we learned the lessons about technical best practices. And although not all of them are perfectly implemented, we in principle know a lot about what we should do. So what will go wrong in other areas of the project? When I started with CRG, I made a list of things that happened in the development of Aspect that we didn't quite expect and that we had to adjust for. And they generally fall in three categories: interactions between the community and the software, trade-offs between different goals within the community, so what they expect from the software, and leadership and governance problems that we hadn't anticipated. In the first category, you, for example, recognize that the architecture of your software, so the way it's written, can support or hinder community growth. If it's too complicated, then people will just give up at some point trying to use or modify the software. If it's too inflexible, they also can't do what they want to do. So the architecture of a software is an important component for the success. Also, the community mood. So whether people see this as more like a competition with the other members of the community or whether they want to work cooperatively with them, influences the size and the quality of this architecture. If people work together a lot, they tend to spend some time working on improving the underlying infrastructure. While if they think they are competing with all of the other members in the community, they don't want to spend time on that. And finally, the work on the architecture and also on the community is necessary work. But if you are a scientist, then that's not often acknowledged, at least not in traditional scientific terms. Then there's the category of trade-offs between competing goals. And the exemplary case is that you have a decision to make that is good for one member of the community but bad for others. And a traditional conflict is the one between performance for certain tasks versus flexibility for a lot of tasks in your software. Nowadays, we know a lot about how to circumvent these conflicts. There are lots of software design strategies available that can help you mitigate them, like encapsulation, polymorphism, templates, however that looks like in the language that you are writing in. But somebody has to do this work. And it's work, again, that's not often acknowledged. But even if you work around it, you can run into situations where one part of the community has a certain goal, while another part of the community wants your software to do something else or to be optimized for something else. And in this situation, you need to try to align the goals of the community. For example, at developer meetings or at whatever way you find to get the community talking about their goals. Finally, a problem that appears, at least in my experience, quite often is that maintainers, the persons who are most familiar with the software, are actually not most familiar with what users do with that software. Oftentimes, the users have problems that maintainers are not really aware of. Maybe the users just think they are too stupid to use the software, and that's why they don't ask the question. So this is one of the other problems that appears in this category. And finally, under leadership and governance problems, I listed a few random problems that seem to appear quite often. For example, in scientific software projects, you have to assume that you're losing users over time because people move on to other projects, which means you also need to constantly grow your user base. You need to acquire new people, onboard new people into your project. And these new people also need to take on more and more responsibility. Otherwise, you end up with all of the responsibility concentrating on just a very few people who are then overloaded with work. If you're successful with that and you grow your community, then you need to communicate all of the design decisions of the inner circle of developers to a bigger and bigger community. And maybe the tools that you used in the past are no longer sufficient to do that. And you need to welcome these new users into the community. They need to be made to permanent members of the community, which again is work. And finally, the bigger the community, obviously, the more likely it is to have conflicts in your community. Either technical discussions that cannot be resolved or personal conflicts between members of the community. And it is tempting as a maintainer to just ignore them and think that they hopefully will go away after a while. But that's not what usually happens. And so these conflicts need to be managed in some form. Otherwise, you might lose members of your community. So when I made this list of problems, I realized that in some form, all of these challenges are actually community challenges. Either it's about the interaction of the community with the software, or it's about the interaction of the community with the community. So why is community management not in the list of best practices that I showed you earlier? And this is actually all the more surprising because for the general open source software scene, the importance of a community and of community management is widely recognized. There's an excellent website that was initiated by GitHub, but is maintained by a lot of open source maintainers called Open Source Guide, which discusses a few of the technical, but a lot of the social problems of maintaining an open source software project. There's a very relevant book by Carl Vogel, which is called Producing Open Source Software. It's freely available online, in which he spends a lot of time talking about all of the technical challenges of producing successful open source software projects. But at least half of the book is also about the social issues. How do you reach people? How do you keep people in your community? And then there are whole books written about how to organize communities and how to manage communities to make them work. For scientific software, there is some information available and there are some papers that have been written about this, but it's much less acknowledged than for open source software in general. And I think that might be for three reasons, maybe others, but these were the ones that came to mind. The first one is that if we think about scientific software, we often have this concept of technical superiority. The best software will win, and the best software is the one that we should use. And when we talk about software, we just mean the source code, the algorithms, the numerics. The second problem is that we still have a problem of attributing work to software appropriately. There was another IDEAS webinar by Dan Katz a while ago about software citation. I will reference that again. But we, in theory, know how to attribute work on software correctly, but in practice, we are still working towards that goal. And in our community, that leads to something that we call hero codes, which essentially means one person writes this code, and it's his code or her code, and his reputation or her reputation is linked to that code, and nobody else really contributes. In this case, it's clear who made the work for this code. But of course, these codes can't expand beyond what a single person can do. And finally, a third problem is that at least for the codes that I am mostly working with, community codes of a relatively moderate size, the persons who are developing these codes are scientists themselves. And they had an education as scientists, and nobody taught them how to be community managers. They didn't want to become community managers when they started this code. So they also don't really know what to do. How could they? So let's summarize a bit why this community management would be useful. In general, the size of the community, the number of your users, the number of the developers, the amount of the funding that you get, limit the activity of your software project. And of course, there are bounds to this size of the community. For example, if you're working on a very specific problem, then you can only expect to interest all the people who are interested in that problem. But there are other factors that you can influence. For example, the easier it is to get your software and to use your software, the easier it is to grow your community. And the more supportive the community that you build around your software, the easier it is to retain people in that community. And the better the atmosphere of this community, the more happy people are to contribute to your software and the longer they stick around. But having this large community, which allows you to be successful, creates a lot of work. More users means you will get more questions, you will have more feature requests, they will find more bugs that need to be fixed, and you will get more conflicts between these users. So if you were able to efficiently manage a community, you could create a successful software project and save time while doing that. And this was the starting point for BSSC for my project for the BSSW Fellowship. I want to collect knowledge from software projects who have done this successfully, who have built a large community and who have been around for a while. I would like to distribute that knowledge as guides online. And hopefully these guides will help new maintainers to get an idea of what they are getting into and what they can do to prepare, but also help experienced maintainers think again about these questions and maybe have new ideas about what they can do in their projects. Ideally, that would lead to a community, the fancy word, a community of practice. So a list of agreed upon best practices of how to manage a software community, and spread this idea that a software project consists of a collection of source code and the community around it. And in the next part of this talk, I would like to give a little tour through the guides that I am currently constructing. But before we do that, I would like to take another quick break and see if there are any questions.
Yes, we do. And actually, there is a long one here. Let me see if I can parse it. Okay, first, so for developer meetings, is there a recommended format for what topics to be discussed?
Yeah.
Let me continue then.
Okay, sorry.
Do you have small, frequent meetings to focus on a particular topic, for instance, infrastructure, to make sure the discussion doesn't derail to other topics? Or do you have a large, in quotes, conferences with different breakout sessions?
Yeah. So I will come back to the question of developer meetings later in this talk, but I guess in short, I would recommend that if you want to change something about the core architecture, then a small focus meeting might be better. But if you want to form and foster the bigger community, then a bigger meeting with all of the community might be better. These are just general guidelines, but I think that's reasonable.
Okay, another question here. As a, in quotes, hero, how to best, in quotes, step back and encourage more community?
Did you say as a code hero? So as a person?
Yes.
Okay,
yes.
Yeah. So I guess one of the important steps is to, first of all, advertise the code as something that you want to be a community code. So make clear that you don't want to keep it for yourself. You are happy to about all of the contributions of others. And then also try to formalize this a bit. For example, acknowledge contributions by other people. And I will come back to that in a later part of the talk as well. They need to feel that they actually get something out of contributing to the code.
Okay, that's all for now. Yeah, please.
Okay. Okay, so maybe the next part will actually also help with some of these questions. So one of the first guides, or one of the first challenges a new maintainer would face when starting a new project is not to grow a community, but to just create one, like get the first members of the community. And this is certainly a very challenging step, but there are a few ideas that can help with forming this initial community. First of all, it helps if you can define your software's mission. That means the idea what your software wants to accomplish. Just to give you an example, in Aspect, we formulated our mission as to provide the geoscientists with a well-documented and extensible code base for their research needs. I admit that that's not very specific, but it already contains 3 important ideas. We want our code to be well-documented and easy to use, for example, for new PhD students. We want it to be extensible, so it is not hyper-optimized for one application, but it is flexible in its applications. And it's made for the research needs of the community. So we don't focus on only what we want to do, but we try to make it a community code that can do what the members of our community want to do. When you could define this mission, you can think about who you should approach with this code. Are you aiming at people who want to do application science, whatever application means in your context? Are you aiming at people who want to develop methods? Which subdisciplines are most interested in what your code is good at? And which career stage are you aiming at? Oftentimes it's easier to reach people in an earlier career stage, but maybe you have already certain people in mind that you could approach with your code. When you have thought about these steps, then you can try to find capable and committed early users. And it's important that these users are committed because your code is likely still somewhat buggy. It might not be finished. You might be missing features. And if someone just tries your code, they often leave afterwards when they notice that something is missing that they want. But if you can find people who commit to your code, who commit to doing a project with your code, then these people will likely stick around and can even become the most important members of your community in a few years. So I admit that this is just one data point, but for example, of all of Aspect's current 8 principal developers, 7 were at the first user meeting in 2014. And since then, all of them have changed their jobs once or twice, but they are still in our community and work with our code. And when you found this initial community, then obviously at some point you have to just work on your software. But while doing that, you should also keep in mind what these early users want or expect from your software. So don't just focus on your plans with the software. Try to make these early user stories a success, because those are the stories that you can use later to find new members for your community. When you try to grow your software, and in particular when you try to grow a community software that is open source, you will encounter some reservations from members of the community. While many people nowadays agree that open source software and open science is important because you will fix more bugs, so have less bugs in your software, you will encourage more participation from your community, your papers will get more citations, and increasingly funding agencies require you to make your software openly available anyway. And you can see more information about all of this in an earlier IDEAS webinar, 24, Software Licensing by David Bernhold. You still encounter a lot of objections by scientists. And these objections are discussed in more detail in the IDEAS Webinar 21, Software Sustainability. But I would say you can summarize these objections into three categories. The first one is intellectual property. People are afraid that other members of the community could steal their ideas when they contribute them to the software without proper attribution. The second objection is scientific reputation. And this goes two ways. Either people would say, well, other people would apply my software in an inappropriate way, and that would reflect poorly on my software. And the other argument is, if I open my software, then people might find bugs in it and damage my scientific reputation. Obviously, in a perfect world, both wouldn't happen, but it's still one of the common anxieties people have about contributing their code to an open source software project. And finally, and one objection is scientific productivity. If I want to contribute my code to a bigger project, then that will take time, and that is time that I cannot spend on writing papers. There are some strategies around this. One really helpful one is a modular software architecture, like plugin systems or systems where you can withhold a certain part of the software for a certain time, for example, until the publication of a paper, and then merge it later easily into the main software, or allowing multiple versions of the same algorithm so that different people can test different ways and write papers about that. But in the end, it still comes down to convincing people of the benefits of giving to a community project. And that involves finding the right arguments to convince them. One way is to acknowledge their fears, their concerns about open source software, but support some courage in them. Many people know instinctively that it would be the right thing to share their science or their software, but they're just afraid or concerned. It helps to show them the rewards of big, successful community projects. Just think of Python and all its libraries. And it helps to be persistent. Just asking a person once for their newly developed extension for your software is often not enough, but twice or 3 times usually does the trick. Another important challenge that people encounter in community software codes is the balance between doing structural work, maintenance work, helping out with debugging or onboarding new members, and scientific work. As I mentioned before, it's crucial for a software to have a good architecture and to have a good setup, but developing and maintaining this architecture takes a lot of time. And at the same time, the community expects growth, so new features or a new release. And you want to do your science yourself. So this time pressure is a temptation to fudge things, to just do them fast instead of right. And the problem is essentially illustrated by this XKCD cartoon, which says if you start a project, you can either do things right or you can do them fast. But either way, you won't get what you wanted, and you have to start over from the beginning. Luckily, there are a few strategies to work around this. So one is that whenever possible, you can combine work on the structure or the architecture of your code and science. And I have an example about this on the next slide. The second one is to delegate work whenever possible. And not only to decrease the work that you have to do, but also to allow others in your community to grow, to show what they can do, and to take over more responsibility. And finally, as a maintainer, you can be as responsive and consistent as you can, but not more. You have a finite amount of time, and you are not required to spend an infinite amount of time on maintenance work. While these strategies can help, there are still some pitfalls and some things that you should take into account and keep in mind. The first one is, as maintainers, our responsibility is to provide a useful architecture, not to fulfill every wish from every user, even if they expect it. The second one is that time that you spend on building the proper architecture for a scientific study is actually useful time. Don't think of this as a waste of time, because if you build the architecture properly instead of just hacking in what you need for this study, this might provide unexpected windfalls. And here's one of the examples from Aspect. We usually solve the compressible Stokes equations for our models. And there are different ways how you can approximate these equations. We got asked several times to implement a different way than the one that we had implemented initially. And we pushed this out, but finally we decided to do it. And we did it properly by allowing just terms in the equation to be removed and replaced without hacking it into the code. This allowed us to write a study, but also later on it was easy to change the other terms in the equation. And people approached us and wanted to change other terms. And they said, it's so easy to do this in your software because we have the proper architecture in place. One word of warning about this, do not over-engineer architecture. It's hard to distinguish this from the second point, but if you don't see an immediate and worthwhile application, you shouldn't build the infrastructure for it, at least not at the moment, even if it's pretty and you would like to implement it. And finally, as I mentioned, your time is finite. Know your limits. Burnout is a common threat for software maintainers, so much so that the Open Source Guide website devotes a whole section about it, but also for scientists. So keep in mind that your maintaining the software project is at least partly fun for you, and try to keep it that way. Then we come to user and community contributions to your software. Obviously, it's up to the project how much you want to involve your community in your software. But if you want your community to contribute to your project, then the members also need the skills and tools to make these contributions. And for that, you need proper documentation and mentoring of new members. One way to mentor these people or these members of your community is to review their code contributions. And there was a BSSW fellowship project last year by Jeff Carver about the proper form of code review. And I would suggest you check out his results. Keep in mind that you should provide guidance at the level of the contributor. So if it's a new user, don't expect from them to know all of the internals of the software already. If it's a maintainer, you can criticize them all you want. One good tool to distribute these tools in your community are developer meetings. And Aspect had a yearly developer meeting for the last 5 years. It has grown our community significantly, and by now, nearly 40% of our yearly commits are made at these community meetings. Obviously, the number doesn't say much about the importance of these commits, but at least it tells you something about how important they are for us as a project. So these are usually 10-day meetings of 15 to 25 members of our community, which is quite a part of the regularly active community. And we usually meet in a relatively remote location, for example, a big house, live together for 10 days and work on the project. And these are perfect opportunities to onboard new members and mentor them. These members can learn a lot during this time, but they are also expected to contribute to the code. And the senior participants have the task of advising, mentoring, reviewing, and helping these new members, which leaves them usually relatively little time for themselves. So keep that in mind for these meetings. Don't expect to spend a lot of time on your own projects during these meetings. In our experience, at least 20% of the participants should be experienced developers or maintainers, because the time of those people is the scarcest resource during these meetings. And don't plan on rewriting the fundamental architecture of your code during that time. Because everyone is contributing at the same time, you don't want to break compatibility for all of them. You want to implement new features during that time. Try to make the code fit for new applications that the new users want to do, but don't break the fundamental level of your code. Okay. At this point, I want to take another quick break.
Hey, Rene. Yes, we have some questions here.
Mm-hmm.
Okay, so let's see. I see a conflict in management philosophy. On one hand, you want a community where many people contribute ideas. But when there are too many ideas, you cannot move forward. Democracy is very inefficient. Sometimes you need, I'll continue here, sometimes you need a dictator to give a single cohesive direction in order to move forward. In Apple, they used to have Steve Jobs. In a community, there are competitions. Some people want to maintain their leadership. Others who contribute ideas that are not in line with the status quo may get shut down. Would you have any comments? Actually, this was a statement. I don't see any question mark here, but if you'd like to comment on that.
Yeah, I think I can make a quick comment. So yeah. It's certainly right that it's, for some discussions, everyone has to come to an agreement. There has to be a decision. And obviously, there are examples of communities where one person who has the final say about something works. But there are also other examples. For example, the Debian project, where everything is handled democratically. What kind of project you want to form, I think, depends a bit on what you are aiming for. And it might also depend a bit on the industry and the application that you have. I think in terms of companies, it might be helpful if you have one person who decides, because you are faster in deciding, but you take less into account what the community actually wants. So I partly agree, I partly disagree. I think it depends on the project.
Okay, so we have 3 more questions. Would you like to take them now?
Sure, yeah.
Okay, so in your experience, what proportion of scientists only openly publish finished code after the paper submitted versus developed code in the open?
Yeah, that's an interesting question.
Is there a way to encourage more openness?
Yeah, so many people are afraid of contributing their code before they publish the publication, because they're afraid of other people using that code to do the same science or do something else. But in practice, that doesn't happen. At least in our project, I have never seen that happen, because you are the person who knows most about what you wrote. And it's relatively unlikely that people see your code, understand it well enough to do the same study that you're already working on before you finish your publication. Sometimes, of course, it can make sense. I'm not saying this is generally the case, but I would say many people have too much fear of this situation compared to whether it actually happens. And on the other side, I have seen situations where people wanted to use that feature and immediately used it for their publication and correctly cited and attributed everything to you and gave credit to you that you wouldn't have gotten otherwise, because they wouldn't have used a different technique then. So keeping the code to yourself can actually be a disadvantage.
Okay, thank you. So another one, do you have any references that you could recommend for learning and practicing different governance methods? Are there non-software focused resources that you found relevant or helpful?
So there is quite some information about governance models in general open source software projects. I really recommend this book, Producing Open Source Software, that I mentioned earlier, and I have it on one of the last slides again, that discusses some governance models for open source software projects.
Okay.
Yep.
All right, so the final question, I think, for this break here, last question. If not at a meeting, when or how should work on building or refactoring infrastructure be targeted?
If not at a meeting?
Yes.
Okay. So yeah, so what you could, for example, do is to have a focused meeting of only the maintainers or the people who are interested in this refactoring. You could also try to set aside a certain week for a kind of virtual meeting to just work on this topic and work online. That I guess that would be my suggestions.
Okay, please continue then.
Okay. So one of the very common conflicts or social challenges that you will encounter during a software project is the one of feature conflicts. So there are several different ways this could happen. I have some examples on this slide in the next. For example, you could have several groups who want to solve the same problem, but they provide different solutions, different techniques to resolve that problem. And in the worst case, none of this solution is universally superior, so you can't decide which one to accept. If you're lucky and if you have a modular architecture that I mentioned before, then you can allow to implement all of them. This is what we did in Aspect for one of the advection schemes. A slightly different example would be that several groups want to work towards a similar application, not quite the same, but somewhat similar, and they need common technical solutions. If they don't talk, they will all implement the technical solution themselves and then do the application with it. Then you end up with several slightly different technical solutions and don't quite know how to merge them into your code. If you discover this early enough, you can get them to talk to each other and implement the method together and then apply it separately for their application problem. The third example, and maybe the most complicated one, is if you happen to have two users who want to work on the same technique and want to write studies about it. You can still be creative in that case. So for example, it's possible to focus on different aspects of the same technique. For example, one group works on the structure of the code and the parallel scalability, and another group works on the mathematical accuracy and the convergence of the method. In general, it's hard to imagine how you can avoid these kind of feature conflicts in a community project, but you can mitigate their impact slightly by just discovering them early enough, which means trying to efficiently communicate within your community who wants to work on what. And if these conflicts occur, trying to be diplomatic and creative about what kind of solutions you can find for them. Obviously, all of this relies on the fact that the groups share credit responsibly, so acknowledging the work of other people. And this leads to one of the other guides, which is about providing credit for software. There was an excellent IDEAS webinar a while ago by Dan Katz about software citation, which stresses the idea that it's important or increasingly important to give credit for the work on software. Here I want to focus on the fact that software citation is just one way of providing credit. It's an important one for your career, but to keep people engaged in your project, there are other types of credit that are also important. For example, the perceived competence. Other people think you are competent because you're the maintainer of this project. Or the social network that you build because you are a maintainer of that project. The feeling of being useful. All of these types of credit are important to keep up the motivation of your community. And you can further this by giving some public rewards to the members of your community. For example, give them a status as a developer or finally as a maintainer if they contributed long enough. But even without all of these rewards, a lot of the motivation of working on open source software simply comes from needing the software and wanting to work in a good team. And you should try to keep this up, like make sure people need your software, but also let them enjoy working on your team. Specific ways how to do this will depend on the project, but there are some possible ways that you could go. For example, you could set up an automatic newsletter that sends around who contributed to your software in the last 2 weeks. We have that for Aspect, and if you want to set up something for your own project, it's available on my GitHub page. It's just a little Python script. You could include the names of all authors who have contributed for the last release in a release announcement. Some other projects, like the DO2 library, write release papers, which have the main contributors as the main authors of the paper. You can emphasize the community members who implemented the feature in talks that you give. You can hand over responsibility. For example, you can allow write access to the repository for trusted developers. And this leads to a connected topic, the one of supporting growth of your members. So you need help for maintaining your software project, and your long-time contributors want credit for contributing to that project. You can solve both problems by publicly assigning responsibility, either by allowing them write access, by handing over responsibility for a certain part of the code, for just including them in the group of trusted people. You should keep in mind that people grow gradually, so don't give them too much responsibility too fast. And you should establish clear policies of how this happens. For example, in Aspect's contributing.md file, we have laid down the policies for what we expect from people to make them principal developers of Aspect, so that they can actually see and plan what they should do and how we reward this. And finally, it's important to, or another social conflict that often appears is not within your project, but with other projects that are competitors to your project. At this point, just a few general guidelines. Bashing competing projects doesn't help. It doesn't help your community, it doesn't help their community, it doesn't help the relation between you two projects. Try to avoid holy wars that are based on opinions and not facts. Try to keep communications open. You can, for example, meet at conferences, talk about problems that you had, maybe even ask for advice if the relation is good enough. You can offer help if they are having problems with similar, if they are having similar problems as your project. And in general, having competitors is actually an advantage for your project, because you can, for one, you can measure in what areas is your project good, in what areas is your project not as good. But it also focuses you to work on what is specific for your project. And community benchmarks are a great way to do this, to do some kind of comparison. Okay, this is an overview of the guides that I'm currently constructing. If you want to help, I would really appreciate feedback about the guides. I have created a short list of questions that would give me an idea about how the community is managed in your software project, and I would really like to get feedback about that to make these guides not specific to the project I'm familiar with, but to give a more representative view. If you have suggestions for improvements or even want to make an improvement to the guides, feel free to open an issue or a pull request on GitHub, or just send me your feedback personally to my email address. I have a list of resources where you can find more information, and all of these slides will be recorded and available on the website, so you don't need to frantically write down everything. And my takeaways from this talk would be software project is equally a collection of source code and a social network. A successful software project needs a successful community, and effective community management can prevent or resolve many conflicts and help your project grow. Thanks for your attention.